Hi, this is John from Diver's Den. Today I want to talk about nitrox versus air because a lot of times when people are doing the e-learning, they come to me and they don't understand some pretty key concepts, particularly partial pressures and MODs and understanding the gas, physics, and physiology associated with those. So some things I want to talk about specifically are Henry's Law and Dalton's Law and how those apply to those gas physics and how they affect your physiology. So Henry's Law pretty much just states that, if you wanted to put it up on the board, it's solubility equals a factor, and that factor is based upon the gas. It's a solubility factor times the pressure. Well, good thing this isn't college science or chemistry, and we don't have to worry about figuring out how many moles get dissolved in a gas or into a fluid. So what this means is if I have a fluid adjacent to a pressurized gas, that gas can be anything, we'll call it nitrogen, that, and this is a pressurized, we'll say 1 atmosphere, that the number, based upon the solubility of this gas, some molecules or moles are going to get dissolved into that fluid. So that's what Henry's Law states. We don't worry about the number of moles dissolved in diving because it's not really relevant for our cause. So we don't care about this, right? All we care about is the solubility is proportional to the pressure. And why that's important is because we know that at every pressure, the gas is going to be the same number of molecules dissolved into our body. Like this fluid is us, primarily our blood, and then that blood gets transferred to our tissues, which is effectively a fluid. Even our bones and things like that, it gets absorbed into our body at different rates, but it still gets absorbed into our body. Okay? So that's Henry's Law. So it's important to know that Henry's Law just states, hey, if I have a gas adjacent to a fluid at any given pressure, the gas is going to dissolve into that fluid consistently. That's Henry's Law. Dalton's Law says if I have a mix of gases next to a fluid, that the pressure exerted or dissolved into those gases is going to be equal to the total pressure on that fluid. So if I have 1 atmosphere, I have atmosphere, I have gas 1, I have gas 2, I have gas 2 here, right? And it's gonna, the total sum of those pressures is going to be equal to 1 atmosphere. Right, so I have pressure of gas 1 plus the pressure of gas 2 equals 1 atmosphere, because up here is 1 atmosphere. So if I go down to 2 atmospheres, it wouldn't matter. It would still be gas 1, gas 2 is 2 atmospheres. So we went down to there, right? So atmospheres, again, is just another way to measure pressure. It could, atmospheres could be measured in, or pressure could be measured in inches of mercury, which is 760 inches at the surface. It could be measured in 14.7 pounds per square inch. It could be measured in 33 feet of seawater, whatever unit we'll use, but atmospheres are easy because it's 1, 2, 3, 4, small numbers are easy. Right, so say for instance, we have, choose 2 gases. We'll choose oxygen and nitrogen. Nitrogen is an inert gas. Oxygen is not an inert gas. It's metabolized by our body. But nitrogen is not. Nitrogen is inert. It's not used up. It just gets absorbed into our tissues, and then it gets off-gassed by our tissues as we ascend. Right, so it's not used, and that's the gas of concern when it comes to decompression sickness. Right, so say I have 2 gases. I have we'll just start with 20%. I have a 20% O2 So we have a partial pressure of PO2 of oxygen of 0.2, right? Because I'm at 1 atmosphere. Right, so if I'm 1 atmosphere, this is my oxygen and this is my nitrogen. We'll do oxygen as red, I guess, to make it easier. And nitrogen is 0. And if I'm at 1 atmosphere, make this a little bit cleaner. 20% oxygen. This is a little hypoxic. Our normal breathing air is 21% oxygen, but this is going to make the math a little easier. Okay, so at 1 atmosphere, this is going to be 0.2 partial pressure. So this is the partial pressure of oxygen. This is the partial pressure of nitrogen. Okay, and then my partial pressure of nitrogen would be 0.8. Because 0.2 plus 0.8 equals 1. If I were to go down an additional 33 feet to 33 feet total to 2 atmospheres, they would have to add up to 2 atmospheres. So in this case, it doubles. 0.4 and 1.6. 1.6 plus 0.4 is 2 atmospheres. It goes down another 33 feet to 66 feet, or 3 atmospheres. 2 atmospheres, 3 atmospheres. It's going to add another 0.2. So 0.6 is going to add another 0.8. So 2.4. Right? So 2.4 plus 0.6 is 3 atmospheres. Okay, it's going to go down another 33 feet to 4 atmospheres. And the trend continues. 0.8 and 3.2 partial pressures of nitrogen, partial pressure of oxygen, and finally we'll go down all the way to 5 atmospheres. This is 99 feet right here, and this is 132 feet. Right, and then we're at 1 atmosphere, 1 partial pressure of oxygen, and 4 partial pressures of nitrogen. Right, and what kind of controls the rate of nitrogen absorption is the partial pressure of nitrogen. So if you were to kind of graph this, right, this is your percent of nitrogen, or your percent loading in nitrogen, and this is your time, or we'll just say like a really fast gas. So like there's 5 different types of tissues. We'll just say it's like, or there's more than that, but we'll say for a 5 tissue model, like a really fast, soft tissue, like it takes 5 of the half-lives for that tissue, but it would look like this, right? It would look like this as that loads up, but if you went deeper, it'd be even faster, right? If you went shallower, it would be like this. For that tissue to get fully loaded, and your computer kind of cuts you off around like right there for no decompression limits. But that's neither here nor there. But my point is the higher partial differential pressure between this and what is in your body, the faster you're going to on-gas. And contrarily, if your partial pressure of the nitrogen in your body is higher than the atmosphere, the faster you will off-gas. And if you off-gas too fast, that's when microbubbles form in your body, and that's what the bends is and decompression sickness is. So let's look at a gas that's a lot higher. Let's say we're doing a gas that is, the maximum we're allowed to do is recreational divers. It's a 40% oxygen mix. So my O2 and then my nitrogen. So about 1 atmosphere, it's going to be 0.4, and then it's going to be 0.6. At 2 atmospheres, it's going to be 0.8 and 1.2. 3 atmospheres, it's going to be 1.2, and then we're going to be at 1.8. At 3 atmospheres, it's going to be 1.6, and we'll be at 2.4, and then at 5 atmospheres is going to be 2.0, and we're going to be at 3.0. So if you examine the nitrogen column here, you'll note that this number here and this number here are identical. So if you're diving in these two mixes exactly, it would be like diving on a 40% mix at 99 feet is the exact same as far as nitrogen exposure is concerned as diving at 66 feet on a 20% mix. That's great, right? So why would you so that's how we, manage our nitrogen. Like that's it. Why would we not do like 100% mix, right? So we'll get to that in a second, right? So if you're wondering how we manage our nitrogen exposure, there's a tool for that. We call that no decompression limits, right? That's a function of our depth and our time. The deeper we go and the longer we stay, that reduces our partial pressure of our nitrogen and our time exposed to that partial pressure of nitrogen to our body. And that's why it's a no decompression limit, okay? But you might think, well, if I can get this to 0 by breathing 100% oxygen, why wouldn't I just do that, right? If I can make this 0 and I would have no decompression limit at all. Well, that's one of the hazards of oxygen, right? At certain partial pressures of oxygen, oxygen can become toxic, and it's one of the biggest hazards of diving with oxygen, right? At about a 1.6, the industry limit, contingency limit for oxygen is 1.6. Above 1.6, you're in a dangerous spot where you can start going into convulsions. In fact, 1.6 is a contingency limit. It's like going 80 miles an hour in a 70 mile per hour zone, right? 1.4 is going 70 miles per hour in a 70 mile per hour zone. You know you're not going to get a speeding ticket, right? So if you are doing here, you're at your contingency limit, right? If you start going into convulsions, it's called CNS oxygen toxicity. The oxygen attacks your central nervous system and you start going into convulsions. If you're on the surface, it's not a big deal. If you're underwater, you could spit your regulator out and you drowned, right? It is one of the single most hazards, dangerous hazards to a diver in the sport diving community, right? That is like super deadly. It's right up there with AGEs and holding your breath going up while you're diving, right? So you have to manage this risk, right? As we have no decompression limits, that's how we manage our exposure to nitrogen. We have another operational aid to managing our partial pressure exposure to oxygen. Our computers will tell us what our partial pressure of oxygen is, but that's another number we have to remember, and it changes with our depth. So planning that is, you could plan it, but it's just another number you have to remember. So a more feasible and easy way to limit our pressure to our exposure to our oxygen is just putting in a maximum operating depth, because the partial pressure of oxygen is a function of depth. So as we descend, as we go deeper, as the pressure around our bodies goes up, the partial pressure of our breathing gas goes up. So the partial of oxygen goes up, and the pressure goes up. The partial pressure goes up of the oxygen that we're breathing. So we limit our maximum operating depth, or MOD. So hopefully this makes a little bit more sense. And it all starts with Henry's Law and Dalton's Law. You have to understand a little bit about Boyle's Law to understand why this happens. I have another video for that, and I'll include it in the description if you don't understand why the pressure goes up over here the way that it does. So to show you a little bit more of how the advantages of nitrox versus air, I have our pressure pot down here. One of these is set to nitrox, and one of these is set to air. And when I pressurize it, they'll turn on and they'll show you which one is which. But what I'll do is I'll pressurize this, and I'll take it down to 100 feet. It's going to be off scale on here. Each 15 pounds is 33 feet, but you'll see the depth on the computers. And then you can note the no decompression limits on the computers to kind of, they're the same computers. They're set to the exact same personal settings, the same algorithms. They have the same amount of surface interval in between. They haven't been dove in a week or two. So everything is the same, except one is set to 32% and one is set to air. So the maximum operating depth for the 32% is 106 feet on these computers, right? So let's go and see how it goes. Okay, I'm pressurizing it, and that should turn them on. The one on this side is set to 32%, and the one over here is set to air, and they're both at 7 feet. And we'll see which one. Note that the one on the on this side, I don't know if it'll be right or left on the camera, but this one will actually give you a no decompression limit first, around 40 feet or so. Whereas the one on this side won't enter a no decompression, won't give you no decompression until about 50 feet. $60 maybe. So we'll take a look at that real quick. Okay, there's our first point where we have two different no decompression limits, right? At 56 feet, the air computer has a no decompression limit of 55 minutes, whereas the Nitrox 32 has a 93 no decompression limit, and you're most likely going to run out of gas before you reach that no decompression limit. You may have noticed that this one entered a no decompression at around 46, 47 feet, where this one you had an unlimited no decompression limit. Okay? So this is approaching the open water entry level depth limits at 66 feet. You can see the balloon get sucked up in there. All right, so at the entry level, you have an air diver at 40 minutes, and you have a Nitrox diver at 64 minutes. Right, so this is one of the reasons that air divers, or that entry-level divers, have a limit of 64, 66, or 66 feet. Right, it's very, very unlikely, especially if you're on Nitrox, that you're gonna reach a no decompression limit. Even on air, very, very unlikely you're gonna run a no decompression limit, and you're not gonna get narked, and which makes any problems that you come across with equipment or anything, makes it easier to solve. Okay, so let's go ahead and continue. We have 40 something, 42 and 66. All right, let's go ahead and continue to let's go to 80 feet. Overshot it a little. All right, we have 37 and 20, what is that, 23? Okay, pretty significant difference there, but not as a big a spread as we had before. At deeper depths, you're more concerned about your softer tissues getting loaded quicker. Oops, that was fast. Okay, now we're down at 100 feet, and you can hear our depth. Our depth alarm's going off. And we're at 25 minutes and 15 minutes. We're 10 minutes off. But at 100 feet, that's a pretty significant difference. Remember, your air is going a lot faster at 100 feet than it would be at like 60 feet or so, about 4 or 5 times faster, or 3 or 4 times faster from 60 to 100 feet. Right, so let's see even what happens if we go down to the recreational limit of 130. It's a contingency recreational limit. So this computer's, the Nitrox computer is well beyond, look at the 1.6. It's 1.5, 1.6, it's beyond the 1.4. So it's giving me an alarm about the 1.4. But it has 15 minutes and this one has 4 minutes. Okay, so let's go ahead and depressurize. No matter how slowly I try to do this, I'm still gonna make the computers angry and they're gonna send. Oh, so that's, hey, the balloon's blown up. I wonder why. Maybe he's sucking air in. Well, so that is my demonstration and explanation of partial pressures, Henry's Law and Boyle's Law, and how they affect you and your body. Physics and gas physiology is one of my, gas physics and human physiology, it's one of my favorite topics to talk about. Hopefully you have a better understanding. If you have any questions or comments, feel free to ask them in the comments section. And if you liked the video, please smash that like button. And talk to you next time. Daltons, Georgia. Thanks.